Hello everyone and welcome to another lesson. In this video, we will be discussing buoyancy as a continuation on our discussion on fluid statics, especially manometry. Buoyancy is a type of force that arises whenever an object is submerged onto a liquid. What you will see here is the interaction between the weight of the object and the pressure acted by the liquid on the object. Let's start by describing Archimedes' Principle. This principle is the backbone for our entire discussion on buoyancy. It states that when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. We can represent Archimedes' principle with this illustration here, wherein I have a spherical object submerged on a beaker of water. If the object is at equilibrium, meaning that it's not moving or it's moving at a constant velocity, then we can describe two types of forces acting on your object. The downward pull is due to gravity, and that is the weight of the object. It's simply equal to the mass of the object multiplied by g over gc, or the acceleration due to gravity. And the upward opposing force is the buoyant force. The buoyant force arises from pressure differences exerted by the liquid from the top of the object up to its bottom. We are only considering the contribution of pressure on the upper and lower sides of the object, even though pressure is acting all over the object, because we are considering all of the vertical forces. Okay? The difference in pressure from the bottom to the top of the object dictates the buoyant force. Remember on our discussion on manometry that the pressure exerted by a fluid varies on the depths or the height of the fluid. The deeper you go on a fluid, the higher the pressure exerted. So in this spherical object, the pressure exerted at the bottom of the sphere is higher than the pressure exerted at the top portion of the sphere, and that difference in pressure describes the buoyant force. We can describe the weight of the fluid displaced, which determines the buoyant force. This is related to the volume of the object submerged. Simply speaking, we define the buoyant force as being equal to the weight of the fluid being displaced, which is related to the volume of the object. The weight of the fluid displaced is equal to the mass of fluid displaced multiplied by g over gc, or our conversion from mass to force. This is 9.81 newtons per kilogram. The mass of the fluid displaced can further be defined in terms of its property density. The mass of the fluid displaced is equal to the density of the fluid multiplied by the volume of the submerged part of the object. If the object is fully submerged, then the volume submerged is simply the total volume of the object. If it is partially submerged, then we have to determine how much of the liquid is submerged. Substituting the second equation to the first, we define the buoyant force as the density of the fluid multiplied by the volume submerged multiplied by g over gc. As you can see in this formula, the buoyant force is independent of the depth of the object in the liquid. That means that as long as this object is fully submerged, whether it is at the middle of the beaker, at the top of the beaker, or at the bottom of the beaker, the buoyant force exerted is still the same, because the buoyant force is only reliant on the property of the fluid, which is density, and the volume of the sphere submerged. If we perform the force balance on this object at rest or at constant velocity, meaning it's at equilibrium, the summation of forces acting on it should be 0. Therefore, the summation of forces acting along the y, or the vertical direction, is equal to positive buoyant force, it's acting upward, minus weight, it's acting downward, and that's equal to 0. Rearranging this equation, we get that the buoyant force is equal to the weight of the object at equilibrium. That means that this object is not moving. If we apply the definition of the buoyant force from the previous slide, we get the density of the fluid times the volume submerged, g over gc, is equal to weight, mass of the object times g over gc. We can cancel g over gc and rearrange the equation to get the density of the fluid is equal to the mass of the object divided by the volume submerged. And this is actually the operating principle for a hydrometer. A hydrometer is a device that is used to measure the specific gravity of fluids through the principle of buoyancy. You might have seen one of this. It is simply an apparatus with a neck and with a ballast. The ballast is simply a weight attached to the end of the hydrometer, which keeps it vertical, and it also allows the hydrometer to sink to a particular level. The hydrometer inside is filled with air, and it is designed to float in water and in other liquids. The way on how we read the specific gravity of a liquid using a hydrometer is we let the hydrometer sit in the liquid and then we read the level of the liquid to the markings on the hydrometer. If you take a look at our governing equation for a hydrometer, you can determine the density of the fluid by simply determining the mass of the object. In this case, the object is the hydrometer, and also the volume of the object submerged. That is the volume of the hydrometer, which is below the surface of the liquid. If we can somehow determine the volume of this submerged part of the hydrometer and then divide that with the mass, you can determine the density of the fluid. However, most hydrometers don't work that way. Hydrometers are often calibrated with respect to water, which has a specific gravity of 1. If the liquid is denser than water, then this hydrometer would float more, meaning that the buoyant force exerted is higher. But if the liquid is less dense than water, then this hydrometer would sink more, meaning that the buoyant force is weaker. That is the case because the buoyant force is a function of the density of the fluid. To illustrate this, let's solve an example. For this example, we will examine the interaction of a hydrometer with different liquids. A hydrometer, when submerged in water at 25 degrees Celsius, has its neck submerged by 2.3 centimeters from the base. When the same hydrometer is placed in an unknown liquid at the same temperature, the neck is submerged by 3.1 centimeters. Determine the density of the unknown liquid. The density of water at 25 degrees Celsius is 997 kilograms per cubic meter. Now, just by reading the problem, we can already make generalizations if the unknown liquid is denser or less dense than water. The problem stated that when the hydrometer is in water, the submersion of the neck is around 2.3 centimeters. But when we transfer the hydrometer to a different liquid, its submersion is deeper, it's 3.1 centimeters. That means that the hydrometer sank more in the unknown liquid compared to water. So based from that, we can already say that the unknown liquid is less dense than water. Its density is lower than the density of water. Now let's prove that with our solution. The solution to this problem starts with the definition of specific gravity. The specific gravity is defined as the density of the unknown liquid divided by the density of water. Both of these are at 25 degrees Celsius. Based on our governing equation for hydrometers, the density of a liquid is the mass of the hydrometer divided by the volume of the hydrometer submerged. Our numerator is for the unknown liquid and our denominator is the same, but this is for water. Mass of the hydrometer divided by the volume submerged in water. Since we are using the same hydrometer, then the mass of the hydrometer is constant across the two liquids, so we can cancel that out. We will be left with the equation, the volume submerged when in water divided by the volume submerged when in the unknown liquid. Now we know that the neck of a hydrometer is a cylinder, so we can simply represent the volume submerged as the volume of a cylinder. The volume of a cylinder, to review, is equal to pi over 4 times d squared times h. Capital D in this case pertains to the diameter of the cylinder, while h pertains to the height of the cylinder. In this problem, the height of the cylinder is the submersion level of the neck of the hydrometer. So for water, h is 2.3 centimeters, while for the unknown liquid, it's 3.1 centimeters. Let's substitute the definition of volume. This would be pi over 4 d squared times h for water divided by pi over 4 times d squared h from the unknown liquid. Again, since we are using the same hydrometer, the diameters of their neck are identical, so that would cancel together with pi over 4. We would be left with the height of submersion when the hydrometer is in water divided by the height of submersion when the hydrometer is in the unknown liquid. And that is readily solvable. We have 2.3 centimeters divided by 3.1 centimeters. We get the specific gravity. That is 0.7419. The specific gravity is dimensionless because it is a ratio of densities. This value of the specific gravity is actually the reading of the hydrometer. The hydrometer is simply comparing the density of water to the density of the unknown liquid. If we go back to our definition of the specific gravity, this is the density of the unknown liquid over the density of water. So to get the density of the unknown liquid, it's simply the density of water multiplied by the specific gravity. Let's substitute. Specific gravity is 0.7419. You multiply this with the density of water, 997 kilograms per cubic meter. The density of the unknown liquid is 739.71 kilograms per cubic meter. And that is how hydrometers operate. Hydrometers give us a convenient way of determining the density of an unknown liquid in reference to the density of water at the same temperature. And that works through the concept of buoyancy. In the previous problem concerning a hydrometer, we just want to determine the natural submersion of the neck of the hydrometer. That means that there are no other external forces acting on the hydrometer except from the weight and the buoyant force. Let us discuss what happens when there are other forces aside from the buoyant force and the weight. This usually happens for objects that are less dense than the liquid. With that, they have the tendency to be just partially submerged in the liquid. In this sense, we say that the buoyant force is greater than the weight of the object, meaning that if you place the objects onto a liquid, its tendency is to float. The opposite of this, when the weight is greater than the buoyant force, that is when the object tends to sink. Now, to fully submerge this object into our liquid, we have to push on it, or we have to apply an external force, that is the force F here. A good example of this is when you have a volleyball in a swimming pool. This is like you pushing on a ball to make it stay underwater. You are the one exerting the external force to keep the ball submerged under the water. And with that, you are introducing a third force, that is an external force. When you introduce this force, the object attains equilibrium at this position, meaning that the summation of all forces, that is the external force, the buoyant force, and the weight, would still be equal to 0. We can use that to prepare this new force balance, that is the summation of all forces acting on the vertical direction, is equal to the buoyant force minus the force needed to keep the object fully submerged minus the weight of the object, that's equal to 0. Rearranging this equation, we get the external force applied is equal to the buoyant force minus the weight of the object. We can examine two cases under this equation. The first one is when the buoyant force is greater than the weight of the object. That is when the object has the tendency to float. We expect that the external force applied in this case is positive. This means that with the force exerted on the object to keep it fully submerged, then we have a counteracting positive force that wants the object to float to the surface. The opposite of that is when the buoyant force is less than the weight of the object. That is when the object would sink to the bottom of the container. We would get an external force that is negative. That means that as you are pulling for the object to stay submerged, then there is an excess of force that works in the same direction as the weights, and that is pulling the object down. For the case of object floating, this is when the density of the object is less than the density of the fluid. And for the second case, that is when the density of the object is greater than the density of the fluid. We actually have a third case, or a special scenario, wherein the buoyant force is equal to the weight of the object. This means that the object neither sinks nor floats in the liquid. It just sorts of intermingles with the fluid. In that case, based on our force balance, the force needed is 0. Remember that this is external force. So this means that the object is already in equilibrium with the fluid and we don't need any force to keep it on a certain position. And this only happens if the density of the object is equal to the density of the fluid. Let's try to solve an example regarding this. A cube measuring 1 foot on a side is submerged so that its top surface is 10 feet below the free surface of water. Determine the magnitude and direction of an applied force necessary to hold the cube in its position if it is made of cork or steel. The densities of cork and steel are given here, and this problem is given in English units. Our force balance in this case, the summation of forces along the vertical axis would result to our equation F is equal to buoyancy force minus weight. The buoyancy force is the weight of the water displaced, that is the volume of the object multiplied by the density of the fluid. So this becomes volume of the object multiplied by the density of the fluid multiplied by g over gc. And then the weight of the object is simply the mass of the object multiplied by g over gc. However, we can express the mass of the object in terms of its volume and density. So we can rewrite this as the volume of the object times the density of the fluid, g over gc, minus volume of the object, density of the object, times g over gc. From our equation, we can factor out similar terms. Simplifying, this becomes the volume of the object multiplied by g over gc multiplied by density of the fluid minus density of the object. Now, from this governing equation, you can easily see what would be the resulting sign of F just by determining the difference in densities between the fluid and the object. If the object is lighter than the fluid, that is, the density of the object is less than the density of the fluid, F here would become positive. That means that you have to apply a downward force on the object in order for it to remain submerged. In this case, the force applied is interpreted as positive even though it's an arrow pointing down because on how we represented the direction of the force. So in this case, if the F is positive, you have to push on the object. But if the F is negative, then you have to pull on the object in order for that to remain at its position. We can now substitute our given and we can identify the force necessary for the cork and also for the steel. For the cork, that is, the volume of the object is 1 cubic foot because it's a cube and it's 1 foot on the side. Multiplied by g over gc. In the English system, g over gc is 1 pound force per pound mass. And then we multiply this to the difference in densities. The density of the fluid, water, is 62.3 pound mass per cubic feet minus the density of cork, that is 10 pound mass per cubic feet. So for cork, the force necessary to keep it in place is 52.3 pounds force. And this is a downward force. For steel, we do the same. That is, volume of the object is 1 cubic foot times g over gc is 1 pound force per pound mass multiplied by the difference in densities of the fluid and of the object. That is 62.3 for water minus for steel 490. We have a force of negative 427.7 pounds force. This is an upward force. So for steel, we need to pull the cube upward just for it to stay on its position, 10 feet below the surface of the water. If you let go of the steel, it would sink further down and that would remove it from equilibrium. Okay, so it needs the upward maintaining force in order for it to remain at its position. And that is how we applied the concept of external forces to buoyancy. Let's have our last example. A cylindrical glass jar, 6 inches long and 2.5 inches in diameter, is sealed while having air inside at normal atmospheric pressure. If the sealed jar having a mass of 300 grams is placed in water, will it sink or float? If it floats, determine the length of the jar submerged. Let us first attend to the question, will the jar sink or float? To do that, we just have to examine the density of the jar and the density of the fluid. Let's first determine the density of the jar or the density of the object. That's simply the mass of the object divided by the volume of the object. Our object is a cylinder, so it's easy for us to determine its volume. That's pi over 4 d squared h. Let's directly calculate the density. The mass of the object is 300 grams. Let's convert that to kilograms. That's 0.3 kilograms. And for the volume of the cylinder, we have pi over 4 times the diameter squared. Our diameter is 2.5 inches. Convert that to meters by multiplying with 0.0254. And this is squared. For the height, that's 6 inches times 0.0254 to make it meters. The density of our jar is 621.58 kilograms per cubic meter. Now, will the jar float or sink? Let's compare the density of the object with the density of the fluid. The fluid, or in this case water, has a higher density than the object. The density of water can be taken as 1,000 kilograms per cubic meter or a little bit less than that. So since 1,000 is greater than 621.58, we can say that the jar will float. The question now is, how much of the jar is submerged and how much of the jar is floating? To answer that question, let's assume that the jar is uniformly floating vertically. If we illustrate that, we can draw it like this. This is our jar. It's our cylindrical jar with the lid, and then it's floating in water. What we want to know is this length. We shall call this x. I will say that x is the height of the jar that is submerged in water. We call this partial submersion, wherein only part of the object is submerged onto the liquid. If you take a look at the forces acting on this body, it's still the same. Its weight is dragging it down, while the buoyant force is keeping it up. The force balance is still the same. The buoyant force must be equal to the weight of the object at equilibrium. Let's examine the terms inside the buoyant force. The buoyant force is equal to the volume displaced, that is the volume submerged of the object, multiplied by the density of the fluid, multiplied by G over Gc. And then the weight is the mass of the object times G over Gc. We can cancel G over Gc, and we are just left with three parameters: the volume submerged, density of the fluid, and the mass of the object. Now, you might be asking, where is x in this equation? Well, if you take a look at the three parameters, the mass of the object is constant, it's a given. The mass of the jar will not change. The density of the fluid is also constant because it's the density of water. So that would mean that x would factor out on the volume submerged, and that is true. The volume submerged, which is in our equation, is not equal to the volume of the jar. The volume submerged is only the part of the jar that is within the line of the water and below it. So that is where x will be useful. The value of x directly tells us how much of the jar is submerged. We can write the volume submerged as pi over 4 times d squared times x. And we complete the equation by multiplying this to the density of the fluid, that's equal to the mass of the object. Rearranging this equation, this becomes x is equal to mass of the object divided by pi over 4 d squared times the density of the fluid. Let us first verify our units if this is correct. We are expecting a unit of meters for our x because remember, this is the height of the jar that is submerged. The mass of the object is in kilograms in standard SI units. Pi over 4 is dimensionless. D squared is meters squared. And then the density of the fluid is in kilograms per cubic meter. Cancel kilograms. And then 2 of the meters would cancel. You would arrive with meters, which is our expected unit. This gives us confidence that our derived equation is indeed looking for a height because its unit is meters. Let's substitute our given. The mass of the object or the mass of the jar is 300 grams or 0.3 kilograms divided by pi over 4 times d squared. Our diameter is 2.5 inches multiplied by 0.0254 to make it in meters squared multiplied by the density of the fluid. Our fluid is water. Let's assume that its density is 1,000 kilograms per cubic meter. The value of x is 0.0947 meters. Let's convert this to centimeters. This is 9.47 centimeters. Let's convert this to inches so that we will have an idea of what percentage of the jar is this. So this is times 100 to make it centimeters divided by 2.54 to make it inches. So this is equivalent to 3.73 inches. The jar is 6 inches long, so more than half of the jar is already submerged in the water. And that is how we approach problems involving solids that are just partially submerged in liquids. Okay, the approach is still the same. If there is no external force, then you go with buoyant force is equal to the weight of the object. If there is a force involved, then simply add that to our expression here. The important thing to remember is the definition of the volume submerged. This is not always equal to the volume of the object. If the object is only partially submerged, then these two parameters are not equal. If the object is fully submerged, then these two are equal. And that's the end of this lesson. Thank you for watching, and as always, keep safe.